this chapter, we will be introducing the concept of integration. In this lesson, we will be looking specifically at how to perform integration by substitution.
Okay, hi everybody. So now we're going to look at the substitution rule. Okay, this is a method of finding the antiderivative of an expression here. Now this only works in certain circumstances here, but this is going to be a method that is going to be fairly useful for a lot of the questions you would get at a high school level here, even into first year university here. Before I get into the actual rule though, let me just show you an example here. Let's say y is equal to let's say the square root of 3x to the fifth plus x to the fourth. Something like that, okay? Now, if I was to say find y primed, okay, then what I would do here is I know, first of all, I would rewrite that as 3x to the fifth plus x to the fourth to the 1/2, okay? Because I prefer to work with rational exponents as opposed to the radical symbol here. So now if I take the derivative, I know I'm going to bring that half down. So it's going to be 1/2 3x to the fifth plus x to the fourth, okay, to the negative 1/2. And then I'm going to multiply by the derivative of what's in between those two parentheses here, because really what I've got here is a composition of functions here. I've got the square root, and then composed within it here is this 3x to the fifth plus x to the fourth. And the derivative of that is going to be 15x to the fourth plus 4x cubed. Okay, so there's my derivative. And I might clean that up even just a little bit and make that 15x to the fourth plus 4x cubed all over 2. And I might even go back to the original radical notation and get this right here. So the derivative is going to be 15x to the fourth plus 4x cubed all over 2 multiplied by the square root, 3x to the fifth plus x to the fourth. Okay, that being said, if I was to now ask you this, what is the integral, and I'm going to leave this as the indefinite integral, of 15x to the fourth plus 4x cubed over 2 root 3x to the fifth plus x to the fourth dx. Okay, so I'm identifying that the independent variable here is x, and I'm taking the antiderivative of this whole thing here. I now know that that is going to be the square root of 3x to the fifth plus x to the fourth. Now, I know that right now because I just took the derivative and I'm asking you to go backwards, so that's a pretty easy thing to say here. But if I was to just give you this, if we hadn't have gone through this process right here, when I look at the derivative here, I used the chain rule to get my derivative. And now what I'm asking you to do here is to take the antiderivative, okay, the indefinite integral. Oh, sorry, and I forgot my forgot my plus c. Woo, that is bad there. I need to remember that plus c when I'm doing an indefinite integral. But anyway, the point I'm trying to make here is one of the things that you want to be able to do is recognize when you're looking at the result of the chain rule so that you can undo the chain rule. And really the way that pops out here is when you notice that part of the function, okay, is the derivative of another function here. And bear in mind here, when you take the derivative using the chain rule here, I've got a composition of functions here. In my derivative, I still end up with this composition of functions here. So I can still see this little bit of a composition here. And what I'm noticing here is this part of the function is the derivative of this part. And noticing that is the key to making the substitution rule work. So here's the substitution rule. Okay, so substitution. If u is equal to some function of x, okay? Then, and here we go. Now this is going to get a little messy here, but I'm going to explain it in a bit here, but it's going to get a little messy just for a moment here, so kind of bear with me here. This is going to be the integral of f of g of x multiplied by g primed of x dx. Sometimes that's not always easy to notice. Sometimes it's quite easy to recognize, but not all the time. that is going to equal to the integral, okay, of f at u du. That is the substitution rule. Now, right off the bat, you might look at that and say, great, thanks, so useful. Yeah, until you actually see an example or two, that actually doesn't make a whole lot of sense. So let me go through and do a few examples with you to illustrate how this works. But bear in mind that, again, this is what we're doing here is I'm trying to recognize when there was a composition of functions, okay, that required the chain rule, and I'm coming up with an approach that allows me to undo that and go backward to the original function here. Now, I should state this right up front here before I get into the examples. There will be many of you out there that look at this and think, well, why would I bother doing the substitution? I can see clearly where I need to go with that. That's awesome. That's absolutely fantastic. I would, however, for those people, advise that you still get comfortable with the idea of substitution, because there will be, in a little while here, there will be questions that you'll be faced with where the substitution is not obvious. And in my head right now, I'm thinking of something specifically called trigonometric substitution. Extremely useful. But if the next few questions that I do to you are really obvious to you, that's awesome. But I suspect that there will be a category of questions you'll get later on that won't be. So you should still get comfortable with this idea. Okay, so let's take a look at this first example here. So it's the integral, or the indefinite integral, of 8x cubed, 1 plus 2x to the fourth to the 1/2 here. Now, one of the things that I advise students to do is when you look at this here, just ignore the integral for a second. If you were to take the derivative of that, would you have to use the chain rule? Well, yes, I would. I'd have to use the chain rule on this part right here. Okay, so what I'm going to do here is I'm going to create a dummy variable. That's what u is. I'm going to create this dummy variable here, and I'm going to change this expression right here from being dependent on x. Okay, so my independent variable here is x. I'm going to set it up so that my independent variable is now this variable here, u. And what I typically do is I'm going to let u equal the function inside the composition here. So 1 plus 2x to the fourth. Now, that is not always the way this works, but it is frequently the way this works. In fact, I will show you an example in a little bit here where that is not actually the way you determine what the substitution should be. But in most cases, this is fine here. So what I'm going to do is I want to rewrite this. So this is going to become, now based on this particular substitution right here, this is going to become the integral of 8x cubed u to the 1/2 dx. Well, okay, right now I'm running into a couple problems here. First of all, I've got two variables here. And secondly, the integral here is still with respect to x, not u. So I need to get rid of this dx here. And actually, it turns out that is easily done because all I need to do here is take the derivative of this. Now, one of the things throughout these videos that I've done here is I've used a lot of the prime to indicate derivatives here. This is one of those places where we might actually want to go back to the Leibniz notation here, and when I take the derivative, make this du by dx is equal to, and when I take the derivative here, 8x cubed. The reason why Leibniz notation is so useful here is because it gives me these differentials. Now, there are a few different ways that you're going to see people organize this. Okay? And by the way, determine for yourself what's most useful to you, how you want to do this, and just pay attention to what your teachers, your professors want you to do. Normally what I would do here is I would straight out solve for dx. And I know there's other ways of doing this, but that's what I would do here. So in my first step here, I would make this du is equal to 8x cubed dx, and then I would divide. So I'm going to get du over 8x cubed is equal to dx. Now sometimes you'll see people that'll take this and say, oh, I've got an 8x cubed here dx. I've got an 8x cubed there dx. And then they will make a substitution right there to cancel. I don't like doing that because sometimes the coefficients don't match and it's a little harder for me to see. So what I do is I just kind of blindly jump ahead here and I'm just going to make this substitution and then I react to what I've got left over. So dx is going to become for me du over 8x cubed. So now I'm dividing by 8x cubed, and in this particular case here, the 8x cubes will cancel with each other. And so I'm going to be left with an integral u to the 1/2 du. So I've made a complete change to this new variable u. Okay? And the antiderivative of that is fairly easy to find. I'm just going to take the exponent, increase it by 1. So it's going to be u to the 3/2, and I'm going to divide that by 3/2. And remember, this is an indefinite integral, so I have to add plus c. Well, now I'm just going to clean this up. Okay, so first of all, that will be 2/3 u to the 3/2 plus c. And I would think, well, this is awesome, this is great, except I'm not done here, because in this particular problem, the independent variable wasn't u, it was x. So that can't be the final answer. What I've got to do is go back up to here and put that back in. So you might even think of this, if you want a kind of a chemistry way of thinking about this, is my u here is like a catalyst. I inject it into my little experiment here. It allows a reaction to happen, but it doesn't become part of it. So what happens here, I'm going to pull that out, and you get this 1 plus 2x to the 4th, okay, to the 3/2 plus c. So I replace that u. And that right there, that is the answer to this indefinite integral, okay? By using this dummy variable u, replacing it, taking the derivative so that I could also replace the differential. So that's the pattern that we're going to follow. Now we're going to do a few more examples here. Okay, here's my next example. It's the indefinite integral of x divided by the square root of x squared plus 1, okay, dx. So the independent variable here is x. Again, I ask, if you were to take the derivative of this, okay, ignoring the integral here, would you have to use the chain rule? Well, yes, I would. And that I would have to use the chain rule on this square root of x squared plus 1. So I think this suggests that the u here, the interior function, would be x squared plus 1. And if I make that substitution here, then what I get is this integral becomes the integral of x over the square root of u dx. Okay, well, this is exactly where I was before here. I've got the problem here. I've got two variables, and the independent variable is still x, and I want to change that over to u because I'm hoping that when I do that, the integral will be a lot simpler. Okay, so the first thing I'm going to do here is take the derivative of this relationship that I've established, and the derivative here is going to be 2x. Now, this is sort of what I was hinting at before, although this isn't maybe the most the most necessary step here. But when I take a look, I see this 2x here. If I start to the process of solving, I get 2x dx. Notice in this case here that I never actually see the 2x dx. I've got the x dx, not the 2x dx. And this is sort of the reason why I typically will simply go through the process and solve for the dx. In a lot of cases, the substitution here is actually pretty clear in most cases, but you will sometimes run into a situation where it's not entirely obvious. And so this method of just replacing the dx, just bringing everything over, getting this expression, replacing with the dx, I have found that to be useful. Okay, so I would make this substitution here. So this is now the integral of x over the square root of u, and then dx is du over 2x. My x's are going to cancel. And actually, I'm going to rewrite this, make it just a little bit easier. I'm going to try to get rid of that rational form there. So this is going to become 1/2 u to the negative 1/2 du. So I'm still stuck with this coefficient here, but that's okay at this point, because remember, one of the things that I can do, one of my rules is I can pull that coefficient right out and deal with that 1/2 later. So this is what I'm working with. Now, how do I take the antiderivative of that? Well, I am going to increase my exponent by 1. So it's going to be u to the positive 1/2. And then I will divide by 1/2. And then remember out here I'm going to have, after this is all said and done, I'm going to have this plus c because this is an indefinite integral. Notice how beautiful this works out because I've got the 1/2 here and I'm dividing by a 1/2, so those are going to cancel each other out. So really my answer becomes u to the 1/2 plus c, which is kind of nice. And then I know, okay, I'm not quite done at this point, I know that u is equal to x squared plus 1. So this ends up really just becoming the square root of x squared plus 1 plus c. That right there, that is the antiderivative that I am looking for. Okay, so here's our next example here. We're taking the integral, and again it's the indefinite integral, of the natural log of x minus 5 all over x minus 5 dx. Now when I look at this, does it look like I would, when I take the derivative of this, that I would have to use the chain rule? Well, yeah, it does. Right there. Okay, when I take the derivative of the natural log, I've got this x minus 5 there. I would have to take the derivative of the x minus 5 inside there. So it does seem like a fairly natural thing to say that this is going to be my u, what I'm going to allow my new independent variable to look like. And so when I make that substitution, I come over here, and I will get the natural log of u, and then notice it's x minus 5 in the denominator, over u dx. Okay? Now, I'm still taking the derivative, my independent variable is still x here, and I want it to be u. So I'm going to take the derivative over here. That'll be du by dx, and interestingly enough, that just becomes 1. So we know that we can simply make this immediate substitution. I can replace dx with du, and so this becomes the integral of the natural log of u over u du. Well, that actually didn't help all that much. These two are basically the exact same thing. The problem that I had here finding the antiderivative is the problem I have here finding the antiderivative. So that didn't work. And this is the example I was referring to before here, where it doesn't always happen where the function within the other function there, that's what you want to set u equal to. Now, in most cases, please don't misunderstand me, in most cases, that is exactly what you're going to do. It's just that in some cases that doesn't work. So what do? Well, you try again. Okay? You just simply try again. So let's take a quick look at this. Is there something else we could let u equal to? Well, now you might say, well, what if I let u equal the denominator? Well, unfortunately, that is still the same thing, x minus 5. So let's let u equal, maybe in this case here, the natural log of x minus 5. And see what happens if we do that. Now, in that case, my integral here, and I'll rewrite this, we had the natural log of x minus 5 over x minus 5 dx. In this particular case here, if we do that, we now get the integral of u over x minus 5 dx. Okay, well, there's no warning bells that jump out at that. I've seen that sort of thing before where I have the u and the x and the dx here. So I know that I got to get rid of my dx. I need the independent variable to be u. So I'll take the derivative of this relationship, okay, because this is my relationship between u and x. And remember, the derivative of the natural log is going to be 1 over the argument multiplied by the derivative of the argument, which in this case is just going to be 1. And actually, I'm starting to feel really good about that because I know that when I solve for dx, okay, I am going to end up multiplying both sides by x minus 5 and both sides by dx. So now that we've got the differential with respect to x written in terms of the differential with respect to u multiplied by x minus 5, granted I could probably have written that in a different order, that probably would have made that look better, but I can do a substitution now and make this u over x minus 5 and multiplied by x minus 5 du. And that is perfect because the two x minus 5 factors cancel, and I'm left with the integral of u du. And you really couldn't have asked for a better integral there, because that's just going to be u squared over 2 plus c. And then after I do my substitution, I am going to get, now I got to be careful with how I write this, because if I write this like this, the natural log of x minus 5 squared over 2 plus c, whoops, sorry, you can't even see that. If I write it like that, okay, if I write it like that, it's not clear whether it's the x minus 5 being squared or what. So what we'll do here, just to make that a little bit easier to read, is we'll just put another set of parentheses there and put the square on the outside. And there you go. That's the antiderivative that we were looking for. Okay, so I'm going to do 2 more examples with you, and these 2 are going to be definite integrals. Okay, so in this case I've got this integral of cos of theta over the sine cubed of theta d theta from pi over 6 to pi over 2. So I am going to get a value at the end here. Now I'm going to do this one in one way, and then I'm going to do another example. I'm going to show you another way of handling it. Now, please don't get concerned about this. I'm not showing you 2 wildly different ways of handling it. It's just 2 different ways of handling the notation. It doesn't matter at all what you decide to do here. So when I take a look at this, and again I ask myself, if I was to take the derivative of that, what would require the chain rule? Well, it's going to be the denominator. And so the interior part of that is that sine of theta. And remember, the outside function is going to be the cube. So I'm going to let u equal the sine of theta. That's going to be my substitution here. And as I've said before, that is normally how that will work. Not always, but normally. So now if I do my substitution here, this is going to get me the integral from pi over 6 to pi over 2. This will end up being the cosine of theta over u cubed d theta. Okay, and this is looking good. I've got 2 different variables here, but my differential is telling me that the independent variable is not u, so I want to change that. So I'm going to come over here, I'm going to take the derivative of this. So du by d theta will equal the cosine of theta, and I love the fact that the cosine of theta popped out. And now, when I solve for d theta, I will get du over the cosine of theta is equal to d theta. And now when I make that substitution, okay, I'm going to come into here. This is going to be pi over 6 to pi over 2 cosine of theta over u cubed. And this will end up being du over the cosine of theta. And the cosine of thetas are going to cancel. And so what I'm left with here, okay, is going to be, and I'm going to write this up. So this will be pi over 6 to pi over 2 u to the negative 3 du. It's just a little easier to write that like that in one line there. Okay, now I will take the antiderivative. That's going to be pretty easy to do because I'm going to increase my exponent here by 1. Okay, so that's going to become u to the negative 2 divided by negative 2. Okay? And I'm going to evaluate that between pi over 6 and pi over 2. Okay, now, at this point here, though, I'm going to have to go back and do my substitution, or put this back in terms of my theta here. So this will end up becoming negative sine theta to the negative 2 over 2 evaluated between pi over 2 and pi over 6. So now I'm back to my original variable theta, which is great. That's exactly what I wanted. So now I'm going to plug these things in. I'm going to simplify this a little bit for myself. So I'm going to make this, here's my first expression here. This will be negative 1 over 2 sine squared of pi over 2, because there's my substitution. So I'm dealing with the negative, I'm bringing that down to the denominator, it's still squared, and I'm plugging in my upper limit. And then this will be subtract negative 1 over 2 sine squared of pi over 6. Now I better look at the screen, make sure everything's on there. And good, there we go. Now I will evaluate. Okay, and so what I'm going to get here is negative 1 over 2. because sine of pi over 2 is 1, squared is just 1, so it's going to actually simplify that down quite nicely. It's quite beautiful, actually. Over here, this will be negative 1 over 2. Okay, got to be careful with this one, because the sine of pi over 6 is going to be a half. Squared is going to be a quarter. So I'm going to have to play with that a little bit. And it turns out, actually, that that's going to work out rather neatly, because this will end up being, if I just look at 2 times a quarter here, that'll be a half in the denominator, which is going to make that a 2. Because of the negatives, that'll be positive 2. And so when all's said and done, the final answer that I get here is negative 1/2 plus 2, or 3/2. That is the value of this particular definite integral. That's a lot of work. Okay, it's a lot of work, but I hope you're not thrown off by the volume of work. It's pretty sequential here, and I'm taking small steps as I go through here. And so that's why this is looking a little large here. But I hope everything makes sense. So again, what I do is I look at this, I look at the interior function, set u equal to what I perceive to be the interior function, make my substitution, and then I got to change the differential, get rid of the theta. So I take my derivative, then I substitute things in. And then here I'm just canceling stuff out, reducing it down to a nice simple expression, take the antiderivative, do my substitution back in, and then I'm evaluating. That's all I got to do. But let's take a look at another example, and we'll do this slightly differently. Okay, so here's my last example that I'm going to do in this video here. And again, it's a definite integral because I've got my two limits here. So I'm going to get a value at the end. I am going to do this one slightly differently than the one I just did. Okay. Now, first of all, it's going to start the same here. I first look at this, sort of looking for where would I use the chain rule. Well, I would use the chain rule here. Whoops, sorry, there. The interior part of that is the x to the 5th plus 1. So that's what I'm going to use. Okay. Now, remember what the goal here by substitution is. I'm trying to take a function that's pretty complicated in terms of x, and I'm trying to basically look at the overall structure of it by simplifying this down. By letting u represent a portion of this, I'm hoping to get a better sense of the layers. And I'm going to use u to help me see what the first layer of integration here has to be. And usually that clarifies what the whole thing is. And I know that might have been confusing here, but if you do enough of these, I think you'll see what I'm trying to say by that. So what I'm going to do is I'm trying to simplify the structure of this. But now what I'm going to do is I'm going to use this equivalence here to simplify even more of the structure of the integral than I have in previously. So this is still the integral of, and notice I'm not going to write the limits now. I'll come back to that in a second. This is going to be x to the 4th u dx. I'm going to deal with the dx here in just a moment, but before I do, let's talk about the limits here. So I am trying to transform this from having an independent variable of x to an independent variable of u. The limits here are x limits, okay? I want to change this whole thing to being about u, so I'm going to use this equivalence to help me figure out what my new limits should be. So if I plug 0 into this, 0 to the 5th is 0 plus 1 is 1. So this equivalence transforms that lower limit to 1. Okay, so maybe I'll set that up here. So u is going to equal 0 to the 5th plus 1 equals 1. U is going to equal, if I take my upper limit here, if I plug that in, 1 to the 5th plus 1, and that's going to be 2. So I will put a 2 up there as my upper limit. Now, in the previous example, when I got through taking the antiderivative, I had to do a substitution back to get my original theta in there. Here, I won't have to do that. So now what I want to do is I've changed my limits. I've done that little bit of a substitution there. Now I want to get rid of my differential. So I'm going to take the derivative. Du by dx is going to equal 5x to the 4th. And like I've done in the past, I am going to spend a moment here isolating the dx, okay, the differential with respect to x. Then I'm going to come back up to my expression. I'm going to make that substitution. So this is now going to be the integral from 1 to 2. x to the fourth u du over 5x to the fourth. Okay, and so now what I'm left with, after the x to the fourth factors cancel there, is the integral from 1 to 2 of u over 5 du. Okay, and that's, whoops. Oh, I'm sorry, the whole time here I've forgotten to put the 5 on there. I'm sorry. That's u to the fifth. U to the fifth. So I know where my answer is supposed to go, and it was quite clear to me that I wasn't going to get there with u there. So I'm so sorry. That should have been u to the fifth the whole time, u to the fifth here. So now when I take the antiderivative of this, this will be u to the sixth over 30 evaluated between 1 and 2. Okay? And I don't need to write the plus c because this is a definite integral. And so now this will end up being 2 to the sixth over 30 minus 1 to the sixth over 30. Well, now 2 to the sixth is going to be 64. 1 to the sixth is just 1. So it's going to be 63 over 30. And I think it's pretty clear that there's a common factor of 3 there. So this will reduce down to 21 over 10. And that's the value that we are looking for. I hope that makes sense. Sorry about forgetting that 5 there. That might have thrown some people off there. But yeah, this expression here was to the fifth. So when I did the substitution, it should have been u to the fifth there. So there's two ways you can do this. You can either transform the limits when you do the substitution, or when you get to this point right here, okay, before plugging in your old limits, if you use the same limits, you have to do the substitution back, so you go back to the old variable there. And then the limits, the old limits, would correspond to that variable. As long as the limits match the variable, you're okay.